section 4.3 because there are a lot of big ideas. Okay, guys. I'm starting now. There are a lot of big ideas, and I think, personally, if I were to make a book, I would have split it up into 3 sections, so that's what I'm doing for you guys. However, so far you might be like, oh, it's not too bad. We're just reviewing tons and tons of pre-cal stuff about what types of functions. Switching x and y, domains and ranges switching, reflections across the y equals x line, one-to-one or invertible, aka inverses are functions or not. Tons and tons of pre-cal review about what types of functions? Inverse functions. And sure, you might not like inverse functions. Sometimes you switch the x and y, don't know how to solve for the y, but they haven't been too bad up until this point, right? The rough thing is, in my opinion, the derivative rule for inverse functions is one of the hardest derivative rules out of all the ones that we learned. And maybe one of the hardest topics of the year to really, truly understand. So I'm going to do my best today as we get into the derivatives of inverse functions, and this is why I'm totally separating this topic from the rest of 4.3. I'm going to try my best to make it as understandable as possible. I'm going to show you a little bit of background as to why the rule is what it is. However, hear me out on this. The book is going to say, and even online, if you were to search for like tutorials, etc., from some of those great math tutors I have on the website, underneath helpful links. To some extent, everybody takes derivatives of inverses differently. Now, does that mean that there's not like a set rule? No, there is a set rule, but there are different ways of thinking about how to do it. So, in homework, you might see, in our book especially, you might see, hey, use this formula. Oh, now use this way. Hey, try to use both ways. And you could go back in the section, you could figure out, oh, they want me to do that. Oh, they want me to use that. Oh, they want me to... I would rather you figure out one way that works for you and use that way instead of stressing about looking at all the different ways and trying all the different ways and trying to be good at all the different ways. Does that make sense? I would rather you find a way that works and stick with it instead of trying all the other ones and in the process of trying all the other ones, like getting confused and then having some like hodgepodge that's not even fully correct. So, I'm not saying ignore the directions necessarily in homework, but I am saying if you look at a formula that you're supposed to use and be like, you know what, I could just do it using this one from class, I'm okay with that. Are we tracking on that? We got it? So, just something to be aware of. There are different ways of looking at these. There are different ways of finding them. You could either try to take the derivative the way it's written. You could try to switch the x and y and solve for y and then take the derivative, or you could try to use a third one. The most important thing for me is just that you figure out a way, or I shouldn't say figure out. I'm going to give you the ways. You pick one that works the best in your brain. Got it? Let's go. Thanks that no one said they actually got what I was saying. Okay, come back. You guys just really tired? I would turn the air down, but I can't because I can't go beyond 76 or else we're wasting energy. Okay, I'm going to do my best. Just going to clap a lot. Okay, so, when we left off on, no, I'm distracting myself. When we left off on Friday, we were talking about pre-cal everything. I want us to camp out for just a second right here. We're going to camp out for just a little second, aka like 5 minutes. Okay, so when I said a function will pass the HLT, wait, what is a function if it passes the horizontal line test? One-to-one or invertible. Which means if I were to do a horizontal line, it can't hit the graph more than once, right? Okay. It'll be invertible, it'll be one-to-one, aka its inverse will also be a function. That's what the actual definition, or at least description, is of those terms. And I said a function will pass the HLT. A function will be one-to-one or invertible as long as the function is strictly monotonic, aka if it's increasing at one place, it's always increasing. Or if it's decreasing at one place, it's always decreasing. Now, how could derivatives help us know whether or not a function is strictly monotonic, strictly increasing, or strictly decreasing? Slopes. What do derivatives tell us? Slopes of the tangent lines. And if the slopes are positive, what's going on with my graph? He's increasing. But wait a minute, can he be 0? Yeah, as long as after 0 he increases more. So if the derivative is always positive or 0, we can kind of like lump 0 into the positives or the negatives because it's okay to be flat as long as it doesn't change direction, as long as it doesn't say, oh hey, it's increasing, oh, it's as long as it changes from increasing to decreasing. As soon as my derivative changes from positive to negative, it just failed. Its inverse will not be a function. We're just going to make everything more difficult if I'm trying to find the derivative of something that isn't even a function. If f prime is always positive or 0, or always negative, or 0. Remember, 0 doesn't make it fail. 0 is okay as long as it just keeps going up afterwards if it's going up before, or keeps going down afterwards if it's going down. If f prime is always positive or 0, or always negative or 0, then my function f is strictly monotonic. And if it is strictly monotonic, then it passes the horizontal line test. And if it passes the horizontal line test, it's one-to-one or invertible, which means its inverse is a function. Now we're going to just take a little time out and do a couple examples because there is a section, I believe, on this in your bookwork. Bookwork? Or handout? Bookwork. Bookwork. In your actual textbook work for homework 18, I believe there are some problems that ask you to do the following. So let's do an example like it. This is an application. An application of derivatives. Figuring out whether or not a function is invertible. So it's in the inverse section because it's, well, invertible means inverses are functions. But this is just an application of derivatives, okay? Example. What if it said, determine, sorry, some of you guys don't like cursive, okay. Determine, we don't even teach it anymore in elementary schools, sad times, right? Why? Determine, because we just type now, who needs to handwrite anything? Okay, determine whether, crazy font, oh dear, just steal someone else's handwriting. Determine whether f of x is one-to-one or invertible or has an inverse that's a function or passes the horizontal line test by analyzing not just this or that, but analyzing the derivative of, okay, A. F of x is equal to 10x to the 6th minus 4x cubed plus 2x minus 7. Letter B, f of x is equal to 4 minus cosine of x, 4x minus cosine of x. C, f of x is equal to 10x cubed minus 4x plus 3, and then D, f of x is equal to 25 x to the fifth minus 9x cubed plus 1. Okay. If this was pre-cal, and if I was like, hey, is he 1-to-1 or not? What would you have to do? Graph it, and then check it, and say, hey, is he going to fail? Now, question, hold on. This first function, do I know exactly what he looks like? A 6-degree polynomial?
Yes.
Wake up. 6-degree polynomial, what's he look like? Well, I know this is his end behavior because he's even and he's positive, right? But do I know if it's going to be a nice parabola or one of those weird W things or like one of those like multiple W things?
Multiple W.
You just made that up. Anyway, are you sure? What changes whether it's a W or whether it's a U or whether it's like a multiple W thing?
The leading.
This part.
Oh, not the other one.
We're not going to really worry about making a sign chart and picking random test values and then figuring out the intercepts and trying to find a graph when we could just find it tells me what? So if I just found the derivative of part A, I'm modeling one for you, letting you go on the other three, and then we'll see if we got it. If I was just to find the derivative of part A, what would I have?
We would have 60 x to the 5 minus 12x squared plus 2.
How does the derivative help? We have something in our notes about 1-to-1 invertible HLT, strictly monotonic, and a derivative. If f prime is always positive or 0 or always negative, wait. So does that mean the x's are always positive or the y's of the derivative are always positive? F prime of x. So those x's or y's? Okay. So if the y's are always positive or 0 or always negative or 0, then this works, which means that's true. And so then you could take the opposite and say, well, if this doesn't work, that's not true, so that's not true. So, what are the y's going to be like for this function? Could they be positive numbers? Sure, plug in 100. That's positive. Could it be negative? Plug in negative 100. Negative 100 to the 5th power is a big negative times 60. A bigger negative totally like runs over those two, right? So therefore, he could be negative, he could be positive. Is he always one or the other? So therefore, F is not 1-to-1. Why? Because F primes signs can change. Not always positive, not always negative, could sometimes be one, sometimes be the other. Now, some of you guys, back when I said end behavior, already knew the answer because, hold on, wait a minute. What's this graph? Oh, well, end behavior right away. Hold on, what's it going to fail? So maybe we could have been able to tell this one a little bit earlier by saying, oh, of course it's going to fail the horizontal line test because they both have to end up going like this. Yep, that's not going to work. But you can also look at the derivative and say his signs are not always, his y's are not always the same, positive or negative, so yeah. Nope. I'm going to pause for just a second. Guys, go find me derivatives. They're easy ones, right? B, C, and D. Find me derivatives. Look at the derivatives. Ponder whether the derivative could be positive, negative, both, neither. That's only if it equals 0, right? And then from that, sometimes positive, sometimes negative, sometimes both, always positive, always negative. See if you can tell me 1-to-1 or not 1-to-1. Okay, when you do that, I'll look. still be thinking about one-to-one or not one-to-one. I'm gonna quickly fill in all my derivatives. You guys can double check. Hopefully we're good on those. Because these are not crazy ones, right?
Right.
Yeah.
Plus sine of x?
Plus,
Plus, not minus, just in case.
right?
That'd be it.
Oh, did I do it again? Hold on. Make him a plus, make him a plus, make him a plus, or else I did have two examples of the exact same thing. Make him a plus, change your conclusion if you must.
Wait, what?
C, make him a plus, or else these two examples are saying the same thing.
Okay.
Did you guys make him a plus? Change the example. I creatively made a bad one. Make him a plus. All right. Letter B. One-to-one or not one-to-one? Ooh. Question. Where's the x for number or letter B? In sine. Okay. What values can come out of sine? 1 to negative 1 are the only y values that can possibly come out of a non-transformed sine, right? So if sine can be anything from negative 1 to positive 1, question, is he always positive, always negative, or a little bit of both? Always positive. What's the lowest sine can be? Negative 1. What's 4 minus 1? Positive. Did you see it? Hold on. Can sine ever equal anything? Look at your sine curve. Can sine go down to anything below negative 1, a normal sine curve? No, it just goes up to 1, down to negative 1. Why? Because it's held within a circle that only has a radius of 1, right? Unit circle. So if he can never be anything lower than negative 1, who's always going to win? The positive. So therefore, he is always positive, which means f will always be increasing, which means he's 1-to-1. Can't ever be negative. How about letter C? Now that I changed him to a plus, if you didn't, please do now. Always positive, always negative, or sometimes both? That's why I had to change the negative to a plus. Always positive. Because whatever I plug in, if I plug in a negative, well, he's positive. Plug in a positive, well, he's positive. Plus 4, no big deal. Always positive, therefore my function is 1-to-1. Why? Can't the last one be 1-to-1?
Because we already had two that were.
Oh.
Funny.
Stop and tell me a reason why. Wait, it's x to the 4th and x squared. Whether I plug in positives or negatives, they're always going to be positives, but there is a minus. Could he ever beat, because he's the negative piece, could he ever beat this one? Your gut reaction is like, no, if I plug in 2 or 5 or 10 or 100 or negative 100 or negative 50, he's always winning, except, what about 0.1? What about 0.1? 1/10 squared is 1/100th, but 1/10 to the 4th is 1/10,000. Is 1/10,000th going to win 1/100th? Throw this function really quickly, either one actually, but throw f of x into your calculator and tell me whether or not he fails the horizontal line test. Well, I know he does, but look at it in your graph real quick. Does he fail the horizontal line test for little baby x's? Does he fail? Just for a little bit? But does he still fail? Yeah. So just be careful. Sometimes the logic is really easy. Ooh, always positive. Sometimes it's kind of like, what? But maybe you can get there, always positive. But sometimes it's like, always oh, never mind. Just be careful, okay? Anyway, an application of derivatives. If the signs of the derivative are always the same, whether it's always positive or always negative, it can tell me the original is 1 to 1. If the signs change, well, all bets are off, it's not. Any quick questions before I change the slide? This literally is homework help, but it's also an application of derivatives. Josh, go.
Oh, I was gonna say for letter C, so if it was like -4, it would have.
Yeah, hence why my example was bad. Because if I had plugged in like 0 minus 4, it would have failed. Wouldn't have been 1 to 1. Dai, go ahead.
Is there letter D? How can it be negative?
Oh, pull out your calculator, plug in 0.1. Yeah, try it. Plug in 0.1, you'll see. And you're like, no, always positive. Well, for numbers greater than 1 or less than -1, maybe even some of the decimals, but 0.1, 0.2, 0.3, some of those are going to fail. But check it. Don't just accept what I say, right? Be discerning. That's the Bible. Okay, come back. This is where we ended last Friday. And we were talking about a differentiability problem. And our differentiability problem said, if f is differentiable, continuous, and increasing, then f inverse will be continuous, increasing, differentiable, but not where f has a what?
0.
Not a 0, but a horizontal tangent line. If f prime of a certain x value, I'm just going to say c, is equal to 0, if there is a place where f prime of c equals 0, then there will be a place where f inverse prime does not exist. I'm actually going to show something though, even though this is not the greatest example. I'm actually going to show you why I wrote this funny thing after that down here. Let me show one more example. So if I had an f of x, and let's say he was somewhere removed, like he wasn't just at the origin. And let's say that he was just like a cubic. That's not going to have a horizontal tangent. Hold on. I need to make him flatter. Now he's even worse. You guys get the point, right? Okay, horizontal tangent at C. Question, where would I shouldn't say where would. Question, when does f have a horizontal tangent? When x equals c. When would f inverse have his vertical tangent line? That's what you would think, right? Well, if f has his horizontal tangent line at c, then f inverse has his vertical tangent line at c. But the problem is, what's f inverse look like? It's not here. Where is it? Instead of x being c, where's f inverse? So does f inverse have a vertical tangent line? Yes. Does it happen at c? Yes. But does it happen at x equals c? Ooh. When does it happen? When? Why does that make sense? Because what switches for inverses and originals? X's and the y's, and that's where the derivative is going to get messy. That is the one singular thing that's going to make it confusing. Let me pause for a second. I gave you at least an idea. F's slopes are going to be related to f inverse's slopes, but where f, the x value where f has a certain slope going on, his inverse is going to have something related to that slope, but at a totally different x value. We're going to come back to that picture in just a second. All right, we're going to find the rule. We're going to discover the rule. We're probably gonna have to end here, but you guys have plenty of homework on the handout, that's pre-cal review. Guys, the handout has 3 sides of problems, 2 of them are pre-cal. Derivatives don't even show up to the 3rd side. Your book is gonna have some places with derivatives of inverses, but there are also some of the strictly monotonic one-to-one, check the signs of the derivative things, okay? So even though this homework is not due until Monday, you can have some fun with pre-cal review, even if you don't get the derivatives. Okay. If I wanted to find the equation of the tangent line, what do I do?
Plug it in.
Plug what in? I have him. A is going to go
Right there.
because he's an x value of f. Some of you are already like, oh no. Because if he's an x of f, that means he's a y of the inverse. Hold on, come back. What goes here?
B.
This is x, right?
Oh.
If that's an equation times an x, that's going to not be a line at the end. That's going to be like a quadratic or a cubic or a square root. I don't want the general derivative. I want the
How'd you do that?
specific derivative. Oh my word.
How'd you do that?
Magic.
Okay. Yay. Thank you, thank you, thank you. Hey, come back. I don't want the general derivative. And some of you are making this mistake, and as you work on test corrections, do
Mañana.
tomorrow, you might find that if you put f prime of x, it didn't work because I need the slope of the tangent line at the points. I have to plug in a. Okay, equation of tangent line. Why is it a derivative? Because the slope of the tangent line is the derivative. Okay. What if I wanted to try to find the equation of the tangent line to f inverse? What would I do? Switch the x and the y, but hold on, this y is no longer the y of the f, it's the y of the inverse. I'm just going to put -1 so that we note that. Minus a. Wait, why does it make sense that the y's would be with the a and the x's would be with the b? The inverse. So the inverse is going to have instead the point b. A. But is this written like a tangent line should be written? What should be on the left-hand side by himself? The y minus the y coordinate. What should be on the right side? The x minus the x coordinate with the m. Oh, I have to move around stuff. Question, what do I need to move? Who doesn't belong? The m, because the m is supposed to go with the x's. When I divide, I multiply by the reciprocal. So if I rewrote this thinking about the commutative property of equations, I could say y inverse is the y of the inverse minus a equals 1 over f prime of a times x minus b. Question, who's chilling in the derivative of the inverse's spot? Wait, where does the derivative show up in a tangent line? The slope of a tangent line to a function is the same thing as the derivative of the function at his x. The derivative of the inverse will be the reciprocal of the original slope, but at the original's x or the inverse's y. That's where it gets hard. I'm going to pause for just a second and write down a nice little, okay, pretty, we'll make it pretty, it's a rule. Ready? That was all just discovery. The bell rings, give me a couple seconds. Do I have one more minute? Please say yes.
Yes.
Thank you, Lord.
Yes.
I wasn't calling you Lord, I was saying very good. Come back. Okay, ready? Derivative of the inverse. If I want to find f inverse multiplication of x is going to be the reciprocal of f prime of stink. The x of the inverse is the y of the original. And I need the x of the original, which would be the y of the inverse. Another way of looking at it, if you don't like all the inversey stuff, is you can think about it with f's and g's, where f is the original, g is the inverse, so g prime of x is equal to 1 over f prime of g of x when, as long as f prime doesn't equal 0. Woo! That's going to be forever card number 14, but we're going to practice him. We're going to example him. Can we example him? Exemplify? I don't know. Him tomorrow. So come back. We'll study derivatives, but homework tonight, work on pre-cal. Bye, guys.
Pre-cal.
Pre-cal review, right?
Pre-cal,
Not
right.
pre-cal homework.
Right.
Pre-cal site.
Where do you eat now? More pre-cal.
I know, but the inverses are so nasty.